Hey, welcome back to Doc Onko's Physics Lessons. My name is Keith Onko, and today what we're going to be doing is taking a look at Faraday and Lenz's laws. This is the video lesson. In other videos, what we'll be doing is solving problems, but today's session is just going to be the lesson itself. We'll do maybe a few different examples, but major examples will be done in other videos. Up to this point, what we've looked at is the interaction between electricity and magnetism. And there's absolutely a relationship between those two. We've shown that in a current carrying wire, there's a magnetic field that surrounds that wire. When a current carrying wire is in a magnetic field, there's a force on that wire due to the interactions of the magnetic fields. Well, in this section, what we want to do is we want to take a look at what happens when we have a changing magnetic field. We've seen that an electric current can create a magnetic field, but will a magnetic field, or some aspect of a magnetic field, also create an electric current? And the answer is yes, it will. So what we want to do is we want to take a look at some of the experiments that were done several hundred years ago by Michael Faraday. And he was a very inquisitive person. And what he did was he did a lot of different things in laboratory in London. And one of the things that he did was he had a setup like the one that we see on the right-hand side of the screen. And what he did was he hooked up an old-style battery on the left-hand side of the screen to a magnetic iron core. And that's this round thing. Whoops, switch to pencil mode there. Let's see what we got here. That's good. This round object right in the center here is just a piece of iron. It's a round piece of iron that's continuous throughout. And what he did was he attached a wire on the left-hand side and wrapped it around a whole bunch of times, probably more than is shown in this picture here. And then connected it to a switch and then back to the battery. And then on the right-hand side, what he did was he also wrapped a wire around a whole bunch of times, and he connected it to something called an ammeter, or he connected it to a galvanometer. All right. A galvanometer is something that we can use to simply measure whether there is an electric current or an electric voltage present. Okay. It won't tell us how much, it'll just tell us that there's something there. All right. Now notice that the two wires are in no way connected. We do not have an electric circuit, right? Because the wires on this side are isolated from the wires on this side. They are coated with plastic or rubber or something, so they're totally insulated wires, right? So it's not like we have bare wire on the left-hand side and bare wire on the right-hand side, and the iron core is going to conduct, because it's not, right? It's not going to conduct electricity. So these are coated wires. Well, what he did was he closed the switch and then looked at his ammeter. In his case, it was a galvanometer, and he didn't see anything, right? Because he wasn't looking at the galvanometer at the same time as the time that he actually closed or opened the switch. But then in subsequent attempts at doing this, he closed or opened the switch and he happened to see the meter actually move. It either moved to the right or it moved to the left. But when the switch was closed, right, and stayed closed, or open and stayed open, the meter did nothing. It was only when there was a change, right, in the current, right, there was the current actually started traveling through the wire, or the current stopped traveling through the wire, that he got a reading in his galvanometer on the right-hand side. So what happened? What was going on? Well, we happen to know that from what we've already studied about solenoids, because this coil of wrapped wire on the left-hand side here and the coil of wrapped wire on the right-hand side is something called a solenoid. It's just a bunch of loops of wire around a piece of metal. In this case, it's iron. And what happens is when we connect this to a voltage source, we get a current to flow. And when a current flows through a coil of wire, what do we get in the middle of that wire? Well, we get I'm going to see if I can draw it right in the middle there. We get a magnetic field, right? And so I drew that in red. So when we have current traveling through the coil of wire on the left, a magnetic field is created in that coil of wire. Okay, well, what does the iron core do? The iron core allows that magnetic field to continue through the core. Okay, so what happens is the magnetic field that gets created on the left-hand side travels through the core, and we now have a magnetic field on the right-hand side. And so what's happened in the coil on the right-hand side is there was initially no magnetic field. But due to the magnetic field that is induced in the left-hand coil, we now have a magnetic field that has been created in the right-hand coil. Well, coils are funny things, okay? And coils are kind of like old people. They don't like change. In fact, many people don't like change, so I don't mean to pin that just on old people. But many people don't like change. Well, coils are just like those people. They don't like change. And specifically, they don't like magnetic field change. They don't like magnetic field changes inside of their coils. So what is that coil trying to do? Well, that coil, apparently, what Faraday found, was it's going to try and create a magnetic field to oppose that change. So the magnetic field initially was in the direction of the red direction. Well, the coil created a magnetic field in the opposite direction to try and oppose it, to try and maintain its status quo, if you will. And so in creating that magnetic field, all right, we now have a magnetic field through our coil. Well, we know that if we have a magnetic field through a solenoid, there must be a current flowing through that solenoid or through those loops of wire. And this is the this is the current that was detected by the galvanometer on the right. So anytime there was a change in the magnetic field on the left-hand side, okay, which then continued through to the right-hand side of the iron core, it created a change in this loop here on the right-hand side. The loop does not like it because it does not like change, and so it created a magnetic field to oppose the magnetic field that was changing inside of its inside core. Okay, and so this is why we get a current anytime we have a change in a magnetic field inside of a loop. And this is called Faraday's law, and then later on Lenz's law. Okay, so let me just scroll down here a little bit. So that's the basics behind Faraday's law. So let's take a look at what happens when we take a magnet, and we have a north end here, we have a south end. So we get the north end, we've got the south end, and we've got a simple wire loop here. And initially, there's no magnetic field inside of that loop. But what I'm going to do is I'm going to move my magnet to the right-hand side there, and I'm going to create a magnetic field inside of my wire loop. Well, what did I just say? I said that our loop does not like change. All right? So by moving the north end of this magnet to the right, I am introducing a magnetic field, right, that's going to the right because the lines always leave the north side of the magnet. I'm introducing a magnetic field into the coil. The coil becomes unhappy, if you will. All right. What's it going to try to do? It is going to try and create a magnetic field going in the opposite direction. Okay? And it's never going to totally succeed, but it's certainly going to try. All right? And so it's going to try to create that magnetic field going to the left in this case. Well, I would like to know what the current direction is going to be in my wire loop. And guess what? I'm going to have to use a right-hand rule once again. Except the right-hand rule that I'm going to use this time is the one where my thumb points in the direction of the magnetic field and my fingers are going to coil in the direction of the current. And this is a 3D kind of thing, so it becomes a little bit difficult, but stick with me if you can. So in the picture that I've got, the magnetic field is going to the left. So I'm going to point my thumb to my left. All right. So what's going to happen? My fingers are going to curl down in the back and up in the front. Hopefully you can see that. So they're going down in the back and they're going up in the front. Okay. Well, if I apply that to the loop that I have, it appears as though this is front, right? And this is back, okay? And sometimes it's difficult to figure out when you're looking at something like this, what's in the front and what's in the back. But it would appear as though those are in the back and these are in the front, okay? If you want to describe this more accurately, or where you can't actually make an error in determining what you mean, you could just say current is going down in the front and up in the back. That way there's no mistaking what it is that you mean, okay? So we have to use a right-hand rule, and it's the right-hand rule where our thumb points in the direction of the magnetic field and my fingers are going to curl in the direction of the current. And we can figure out just what the direction of the current is going to be in our loop. Now, keep in mind that the magnetic field that I'm going to use the right-hand rule on is not the magnetic field that's being introduced. It's not this green magnetic field here, right? It is the orange magnetic field that gets induced. Okay, so it's not the magnetic field that that is created by the magnet itself. All right, it's the magnetic field that is induced by the coil. That's what I'm using my right-hand rule for. So my thumb points to the left, right? And again, down in the back, down in the front and up in the back. Okay. Okay, so we've determined that we have some kind of a change in the magnetic field inside of the loop. So we're going to introduce a new concept here, and it's the concept of magnetic flux. So magnetic flux. And all magnetic flux is we take a look at the magnetic field, right, shown here or depicted here by the lines, the red lines going from left to right, right, through some surface area. Okay, and the surface area here would be the square rectangle there. It's actually a square, okay? And so what's the definition of magnetic flux? Well, the definition of magnetic flux, and it's given by the letter phi or phi, depending on how you pronounce it, is the strength of the magnetic field times the area of the surface that it's going through times the cosine of theta. All right. Now, the cosine of the angle here is unfortunate, and it confuses many students, because if you look at the picture here, right over here, what I've got is I've got a surface area with a face, and I've got a magnetic field, and it certainly looks like the magnetic field is perpendicular to that surface area, doesn't it? All right. Well, if it's perpendicular, what's the angle? The angle's 90 degrees. Well, what's the cosine of 90 degrees? Well, it's 0. Well, that doesn't make a whole lot of sense, does it? No, it doesn't. And this is the trick, all right? The trick here is that we're not taking the angle theta here between the magnetic field and the actual surface area. We're taking the angle between the magnetic field and a vector coming out of the surface area that is perpendicular to the surface area. Now, that is confusing to many students, and the question is, why on earth did they do that? And it's just the convention that's used in physics, and if we were doing calculus-based physics, you'd understand better, or we can make it more clear. But let's just stick to this, that it is not the surface area that you want to take the angle from. It's not the magnetic field versus the surface area itself. It's the magnetic field versus a vector coming out, all right, normal to the surface area. And that's what the angle theta is, okay? So in this case, let's say I had a magnetic field strength B equal to, and I'll use my old favorite number, 0.05 Tesla. And I had an area here, let's say that square is 10 centimeters on a side, so the area would be equal to 0.1 times 0.1, 0.01 meters squared. Okay, and so what would my magnetic flux be in this case? Well, it would be 0.05 Tesla times 0.01 meters squared. Whoops, forget the units there. And that would be 0.0005 Webers. Okay, the unit of magnetic flux is the thing called a Weber. Okay, and that's really all there is to figuring out magnetic flux. Now, over on the right-hand side, you can see a situation where the magnetic field is not perpendicular to the surface area. So in this case, we would have to take into account the angle theta, and it would generally be given to you, and you would just figure out what that angle is. Okay, but remember, the angle is the difference between the magnetic field itself and a perpendicular or normal line to the surface area. Okay. All right, so what we actually saw, all right, or here's another, before we get to that, here's another example of magnetic field lines being perpendicular and partial, and actually no magnetic field lines passing through a surface. Over here what we have is we have magnetic field lines perpendicular to a surface area, right, at this example right here. In the middle we have something in between, right, and so we have magnetic field lines passing through a surface area, but the surface area now is less than what it was when it was perpendicular. Right? We have a smaller amount of surface area that the lines can actually travel through. The line, if you look, the lines on the edges here no longer travel through the area, and so our flux is going to be less. Over on the right-hand side, right, our surface area is here. How many of those magnetic lines are actually passing through our surface area? Well, none of them are. Right? And so our magnetic flux over on the right-hand side in this example would actually be 0. And we'd have the greatest magnetic flux over on the left-hand side. All right, so that's magnetic flux. Now, what we noticed, though, was that when we had that changing magnetic field, we had an electric current that was detected in the galvanometer. And so there must be, if there's electric current running through a wire, there's got to be a voltage pushing it through that wire. And indeed there is. And we give this funny letter E here, and it stands for EMF, or electromotive force. All right, it's the same as voltage. And the equation that we have is electromotive force, or voltage, is equal to the negative of the change in the magnetic flux, because remember, it's not a constant magnetic flux that will create, or constant magnetic field that will create a current in the wire, but it's only a changing magnetic field, and thus a changing magnetic flux, that will cause a current in the wire. Okay, divided by the amount of time, or how quickly that change is made. Right? So the voltage that we get is dependent on the change in the magnetic flux and the speed at which it's done. Okay? And the equation on the top here is for a single wire loop. The equation on the bottom here is a more general one, and that's for a multi-wire loop. The electromotive force, the voltage that is induced in the wire, is equal to the negative of N, which is the number of wire loops, times the change in the magnetic flux divided by the time. Okay, so let's do a little example here. Let's say that over on the left-hand side we have a magnetic or a bar magnet moving into and then out of the coiled wire. Okay, so we have a coil of wire and we're going to move it in and out. And let's say N, the number of coils in our wire, is 100. Okay, and the initial magnetic flux is 0 because there's no magnetic field, and we'll make believe that that bar magnet is very far away. And then the final magnetic flux we're going to have to actually calculate. Okay, so when we get the bar magnet close enough, we're going to say that we get the magnetic field B is equal to well, we'll just make it my old favorite number, 0.05 Tesla. and we're going to make the area inside the wire loop equal to 0.01 meters squared. Okay, we don't know what the radius is, we're just going to make up a number there. All right, and the time that it's going to take to go from zero magnetic flux to whatever our final magnetic flux is going to be, we're going to say that is 0.05 seconds. All right, and we would like to know what the EMF induced in our coil of wire is going to be. Okay, so let's first figure out what our final magnetic flux is going to be. All right, well, it's going to be B, right, 0.05 Tesla, times the area, 0.01 meters squared. All right, and the magnetic field is perpendicular to our surface area, and so the cosine of theta is going to be 1. And so our magnetic flux turns out to be 0.0005 Webers. So that's our final magnetic flux. So if I want to figure out the EMF, or the voltage, it's going to be the negative of N, which is negative 100 turns, times the changing magnetic flux, where our final magnetic flux is 0.0005, minus 0, because that was our initial magnetic flux, divided by the time that it takes to do all this, and we said that was 0.05 seconds. So it happens pretty quickly. I'm just leaving the units out just to make it a little easier and give you enough space to do this. Right. So when we do this calculation, what we come up with is a value of -1 volts. So that's how much voltage has been induced in our coil. Okay. Now, if I want to know how much current I actually am going to have in the coil at that time, well, let's say that the resistance of our coil of wire is about 0.5 ohms. Okay, we have a voltage of -1 volts. Okay, and the negative sign is just an indicator as to what the direction of the current is going to be. And so I, using Ohm's law, is going to equal V divided by R. So that's going to be -1 volts divided by 0.5 ohms, and that is equal to -2 amps. Now, are we ever going to really get that much current induced? It would be great if we could, and maybe you would, depending on how many loops you have in your coil. So this is an introduction to Lenz's and Faraday's laws. Please see the videos on the examples that I have, and I hope that helps, and we'll see you next time.